Hi, my name is Ritika, and are you looking for a DSA partner? So you can just join me. Like, it's a bit challenging for me, but I just take a courage and start. So today is day one, and I'm solving apna college data structure sheet, and my codes are generally in Java, and I try to solve all approaches. And yeah, generally I'm just revising everything from basics. So this is my day one, and it's a reminder to you if you're also start and fail, so you can. Oh, these are the questions in the upcoming videos which I have solved today. So yeah, you can just check it out. Bye bye. That's it for today. See you tomorrow. Today we are solving the majority element problems. We are given an array of integer. The majority element is the element that appears more than n by 2 times. It is guaranteed that the majority element always exists in the array. Let us understand all possible approaches one by one. Approach 1, brute force. First, let's understand the brute force approach. In this method, we will pick one element at a time. For each element, we count how many times it appears in the array. If the count becomes greater than n by 2, that element is the majority element. Then we immediately return that element. This approach uses two nested loops. That's why this is not an optimized solution. Because of that nested loops, the time complexity becomes O of n square, and space complexity becomes O of n. That's why this code is not efficient for large arrays. Now, the second approach is hash map. Here we store the frequency of each element. We traverse the array only once. If at any point the frequency becomes greater than n by 2, we return that number. This approach reduces the time complexity to O of n, but it uses extra space because of hash map. That's why this is not an efficient, because it uses extra space complexity. The third approach is sorting. First, we sort the array. After sorting, the majority element will always be present at the middle index. This is because it appears more than half of the time. So we simply return the element at index n by 2. The time complexity of sorting is O big O of n log n. The space complexity depends on the sorting algorithm, or we can say O of big O of 1. This approach is simple but slower than the optimal solution. Now let's discuss the most important and optimal solution. This approach is called Murray's voting algorithm. We maintain two variables, first count and second candidate. Initially count is 0 and candidate is also 0. We traverse the array one element at a time. If count becomes 0, we select the count element as the candidate. If the current element is equal to the candidate, we increment the count. If the element is different, we decrement the count. This process cancels out different elements. Since the majority elements appears more than all other elements combines, it survives till the end. At the end of the traversal, the candidate is the majority element. That's why the time complexity of majority element in this approach is big O of n, and the space complexity is big O of 1. That's why this is the best solution for majority element. Thank you. Now we will understand about missing and repeating element code. So first we initialize two variables, repeating and missing. Now we loop from 1 to n. Numbers are in this range. For each number we set count to 0. We traverse the entire array to count occurrence. If the array element is equal to the current number, we increment count plus plus. If count becomes 2, the number is repeating. And if the count is 0, then the number is missing. Finally, we return repeating and missing element. This approach has big O of n square time complexity because here we are using two loops. Therefore, this is not an optimized solution for this problem. We create a frequency array of size n plus 1. This is our second approach for repeating and missing value. So here we are using hash map. Hashing, not hash map, hashing. So now we traverse the given array here. Next we loop from 1 to n. If the frequency is 2, then the number is missing, and if the frequency is 0, missing. This approach runs on time complexity of big O of n, but it uses extra space because of frequency. That's why this is not a solution for this problem. This is the third approach. We calculate the expected sum of numbers from 1 to n. We calculate the expected square sum. Here we calculated the expected sum of number from 0 to n, and here we expected the sum of square. Now we calculate the actual sum and square sum from the array. The difference of sum gives missing minus repeating, and the difference of square sum gives missing square repeating square. Using these two equations, we calculate missing and repeating. This is the difference, and these are the formula. For missing, we use difference plus sum of missing by 2, and for repeating, we have missing minus difference. And we return repeating and missing. This approach contains constant space, but calculation are complex. That's why this is not an optimal solution for repeating and missing. Now we will see the optimized solution of repeating and missing. First we will initialize XOR as 0. We XOR all elements of the array. Then we XOR all the numbers from 1 to n. Now XOR contains missing, XOR repeating. We find the rightmost set bit. This bit help us divide numbers into two groups. We XOR array element based on the set bit. We XOR number from 1 to n in the same way. Now we get two values. One is missing and one is repeating. We check which value exists in the array. That array is called repeating and the other is called missing value, which is not present. This approach runs in O of n time complexity, and the space complexity is big O of 1. That's why this is the best solution for finding missing and repeating. So we are solving the single number problem. We are given an array where every element appears twice except one. Our task is to find that appears only once. So, the first is brute force. First, we create a hash map to store the frequency of that element. Now we traverse the array. For each element, we update its count in the hash map. If the element is already present, we increase the count. If the element is its count, otherwise we insert it with frequency 1. Next, we traverse the array again. After the frequency of the current element is equal to 1, that element is the single number. So we return it. That's why this approach runs on the time complexity of big O of n log n plus m and space complexity of big O of m, which is not optimized. Now we use the optimized approach. Now let's discuss. First we initialize XOR as 0. Then we traverse the array where we XOR every element with XOR. XOR of a number with itself becomes 0. XOR of a number with number gives the number. So all duplicate elements cancels out. At the end, only the single element remains in XOR. At the end, only the single number remains in XOR. We return XOR as the final answer. This approach runs at the time complexity of big O of n and the space complexity is big O of 1. This is the most efficient solution for single number. Thank you. Now we are seeing the brute force of merge sort of merge to sorted array. So first we create a temporary array to store merge elements. We initialize 3 pointers I, j and k. Pointer I is for nums 1 and pointer j is for nums 2 and k is for temp. Now we compare element from both arrays. The smaller element is placed into the temp array. We move the pointer forward. After one array finishes, we copy remaining elements. Finally, we copy all elements back into nums1. This approach is easy but uses extra space. The time complexity of this program is O of m plus n and the space complexity is O of m plus n. This approach is easy but uses extra space. This is its time complexity, this is its space complexity. The second approach. Here we are using 2 pointers. We use 2 pointers to traverse both arrays. This maintains sorted order. Remaining elements are copied directly. At the end, we store the result in nums1. This approach is clear and beginner friendly, but the time complexity of this program is same as and space complexity is also same as the other. So for this we are now seeing the optimal approach. Now we start merging from end to the end of the array. Now we are seeing the optimal approach. We start merging from the end of the array. The pointer I is the valid end element of nums1, j is the last element of nums2 and k is at the last index of nums1. We compare element from the back. The largest element is placed at index k. This prevents overwriting element. We move pointer backward. If nums2 still has element left, we copy them. This approach uses no extra space. That's why its time complexity is big O of m plus n, but its space complexity is big O of 1. That's why this is the optimal solution. Now I am showing you the solution of buy and sell stock. This is the optimal solution for buy and sell stock. In this problem, if we want to buy any stock, we will buy it when our stock price is the lower, and we sell it when the market price is higher, and the market price this we can't sell and bought the stock in the same day. So we initialize buy price with a very large value. Here, integer dot max value. We initialize profit as 0. Max profit as we buy, that is 0. We traverse each stock price. If the current price is smaller than buy, we update buy price. Otherwise, we calculate the profit. If the profit is greater than the current profit, we update it. At the end, profit stores the maximum possible profit. This this approach works on the time complexity of big O of n, and the space complexity is big O of 1. Now we are seeing the power of xn, compute power of xn. So here is the code. Like, what is compute power of n? Like x to the power n. So here x is 2.00000 and n is 10. So 2 to the power n is equal to the power 0000 and 10 is equal to 1024 decimal 00000. So how we can calculate it? First, we initialize a variable and its name is return, which is 1.0. We use a loop that runs n times. In each iteration, we multiply result by x. After the loop ends, result contains x raised to the power n. Finally, we return result n. This approach is simple and easy to understand, but it is slower for large values of n. The time complexity of this code is big O of n, and space complexity is big O of 1. Let's discuss the optimized approach. This approach is called binary exponential. First, we store n in a long variable to handle overflow. We initialize result as 1. If n is negative, we convert x to 1 by x and make n positive. Now we run a loop until power becomes 0. If power is odd, we multiply result by x. Then we square x and 8 power by 2. This reduces the exponent by half in each step. This approach runs on big O of log n times, and the space complexity is big O of 1. This is the optimized approach for power of exponent.